Chapter 6 is about solutions. In our solubility chapter, we will be learning about the effect of pressure on the solubility of a gas in a liquid. I'm going to tell you about a tragedy that occurred in Cameroon, West Africa that explains this phenomenon. This is Lake Nyos, which is a volcanic crater filled with water in Cameroon, West Africa. And the volcanic rocks are below the water and they produce carbon dioxide through natural geological processes. The carbon dioxide seeps into the bottom of the lake, and the pressure of the water itself allows the concentration of carbon dioxide to build up. Normally, lakes, when the weather becomes cooler, there's a natural changeover from the surface water with the bottom of the water in the lake. Lake Nyos is near the equator, and the temperature near the equator stays warmer. So they didn't have the actual mixing of the layers of the water occur at Lake Nyos. And in 1986, there was a rock slide that occurred. And this caused Lake Nyos to degas, releasing about 1 billion cubic yards of carbon dioxide, which displaced the oxygen in the air around it. So this picture here is showing me a molecule of carbon dioxide. And in the air, we need oxygen to breathe. So we know carbon dioxide is going to be heavier. Okay, so in the atmosphere, the carbon dioxide displaced all the oxygen that people needed to breathe. So the people living in the area for about a 25-kilometer radius from this lake ended up suffocating from lack of oxygen. It ended up killing about 1,800 people. This map shows us where Cameroon is located in West Africa, where Lake Nyos can be found, which ended up killing 1,800 people because of this tragedy. And these people were living in villages and they were raising cattle, and it ended up killing about 3,000 of their cattle as well. And this again was due to this carbon dioxide cloud. So the carbon dioxide built up in the lake because the thing we're going to learn in this chapter is the solubility of a gas increases with increasing pressure. So carbon dioxide is a gas, and the pressure of the lake itself caused that increase for the solubility of carbon dioxide in the lake. And again, normally if the temperature cooled off, then the bottom of the lake would switch with the top of the lake and we'd release all that gas. Because that didn't happen, there was a high level of carbon dioxide, and the rock slide allowed the release of that carbon dioxide. So this is actually a PBS special was done on this event. And in the PBS show, they show the African animals like the zebras and the gazelles coming to the lake to drink water, and they just sort of keel over because they end up suffocating. So this was a very unfortunate event that occurred. In order to prevent this tragedy from ever occurring again, what they've done with Lake Nyos is they went ahead and put this pump into the lake that causes the water from the bottom to be transferred out. So this is called degassing of the lake. So they're allowing the carbon dioxide to be released from the lake. A solution is a mixture of two or more soluble pure substances. They are physically combined, not chemically combined. For example, sugar water. If we look in the beaker on the left, we're adding the sugar. The yellow spheres represent our sugar or sucrose molecules. And then we have our water molecules, the red and gray ones. And then when we mix the sugar into water, we know that it dissolves. And we can see at the molecular level, we still have our molecules of sugar, and we still have our molecules of water. So we did not alter the identity of our mixture by combining our two pure substances together. The pure substances that make up a solution are called the solute and the solvent. The solute is the substance that is being dissolved. For example, if I put sodium chloride or table salt into water, the solute would be the sodium chloride. The solvent is the substance that does the dissolving. So in this case, it would be water. And the beaker on the right is showing us at the molecular level that we still have our molecules of water represented here, and we have our sodium chloride represented by the purple balls are the sodium and the green ones are the chloride. Another way we can define solvent, we could say it's the substance present in the larger amount, because you can have a solution where you have a mixture of, let's say, two liquids. Okay, so the one that's present in the larger amount is going to be what we classify as the solvent. Identify the solute and the solvent in the following solutions. The first one we have is saline solution. This is what is used in IVs, and this is basically just salt water. So we looked at that example previously, and we said what's being dissolved is the salt, and what does the dissolving is the water. The appearance would be, is it a solid, liquid, or a gas? So saline solution would be a liquid. Vodka is comprised of mostly water, and then it also has alcohol. So the one in this case where we have two liquids that is present in the smaller amount is going to be our alcohol, and the larger amount would be water. And vodka is a liquid. Perrier, which is bubbly water that has carbon dioxide gas in it. So this is an example where I could have a gas dissolved in a liquid, and that would be a solution. So my solvent is the water. The carbon dioxide is present in the smaller amount as my gas, and my appearance would be a liquid as well. So this is showing us at the molecular level where I have carbon dioxide dissolved in water. So again, two pure substances mixed together makes a solution when they dissolve in each other. So here are a few more solutions that I'd like to identify, the solute and the solvent. The first one we have is air. So air is a solution. It's a mixture of different pure substances. So what air is made of mostly is nitrogen. That is the biggest component in air, is nitrogen gas, or N2, one of our diatomic elements. And what we need to breathe is O2, or oxygen. So that's going to be the solute because it's a smaller amount. So air is approximately maybe, I'd say about 78% nitrogen, and oxygen's about 21%. And then we have some other gases present in the smaller amount. So you can have more than one solute. So when we exhale out carbon dioxide. So that's another gas you would find in the air. Argon is also present, and there's a number of other gases present in smaller amounts. So the appearance for air we know is a gas. So this is an example of a solution that is a gas. Dental fillings, and I'm looking at the one at the top here, the silver fillings that you may have in your mouth, I have a few of those in my own mouth, are actually a solution. So the solvent for silver fillings is what's present in the larger amount in silver fillings is silver. And the solute, they're actually mixed with a little bit of mercury. And they call these amalgam fillings. Versus the one at the bottom, those would be your porcelain fillings. So the appearance of the amalgam fillings is going to be a solid. The fillings are solid in your mouth, and it's a mixture of these two metals. So I actually have a story to tell you about amalgam fillings my dentist had told me about. She's also a dental instructor at USC, and she said another one of the professors at USC was having a lot of health problems, and she kept going to different doctors and nobody could figure out what was wrong with her. So my friend the dentist said, well, I see that you have all these silver fillings or amalgam fillings. She goes, I'd like to remove those. So she took them all out and replaced those with the porcelain or the white fillings. And after she did that, her friend, the other professor at USC, was absolutely fine. She didn't have any more health problems. And with a one-person experiment, we don't know if these results are valid or not, but my dentist was saying it's probably may have been due to the mercury that's inside the amalgam fillings. And mercury is actually a toxic metal. And it's usually if you're exposed to the vapors over a certain amount of time that it causes health problems. And it's going to depend on the sensitivity of the individual because I have amalgam fillings in my mouth and I haven't had any health problems due to the fillings. So this person was probably very sensitive, but it may have been due to that very small amount of mercury that are in the that were in those fillings. We have one more example down here. What are the solutes and solvent in beer? So let's start with the solvent, the one present in the larger amount. So beer is going to be mostly made of water. The solutes, one example would be alcohol is in beer. And then what makes it bubbly is we have carbon dioxide gas. So those are the solute and solvents in beer. Below is a list of characteristics of solutions. The first one is the distribution of particles is uniform. If we look to the beaker to the right here, the particles we have in here are water molecules and sodium chloride. And the distribution of these particles within our beaker is uniform. The components do not separate. So imagine if I had a glass of salt water. I'm not going to have the salt sitting at the bottom. The components are not going to separate. Or in this example down below, this is a solution of copper sulfate, which copper sulfate is a blue crystal mixed in water. If I make a solution, I'm not going to have the crystal separated to the bottom. They are almost always transparent, meaning I can see through them. The solution can be colored, like my copper sulfate solution down here is colored, but I can see through it. It says almost because we just talked about having an amalgam filling. That's a solid solution, and I can't see through that. You can make solutions of different compositions. For example, different percents, like 1%, 2%, 10%, etc. So in the example in the picture here, we are looking at two solutions of copper sulfate. So copper sulfate, as I said, is this blue crystal. I'm dissolving it in water. The more copper sulfate I add to the water, the darker blue it's going to be. So this would be a higher concentration or a higher percent than the one on the left. It's got a less amount of copper sulfate in it. Another characteristic of a solution is that you cannot separate the solution by using filtration. So filtration is when we have a solid and a liquid together. We can put the solid and the liquid through the filtration apparatus and separate the liquid, and the solid would be left in my funnel where the filter paper is. So we can't use this for a solution. So a solution, we just said, is uniform in composition. So you can imagine if I took my solution here and I poured my liquid through the filter paper, all the liquid would just come out at the bottom. So it cannot be used to separate a solution. The last characteristic of solutions that we'll discuss is that solutions can be separated by distillation or chromatography. This is a distillation apparatus on the left, and a distillation apparatus works by separating liquids based on different boiling points. So in this flask, we have wine which is a solution. Wine is comprised mostly of water and alcohol, about 12 to 13% alcohol. The boiling point of water is 100 degrees Celsius. Alcohol boils around 80 degrees Celsius. And so when we heat up our wine using our burner, that we're going to have the vapors from the alcohol form first. So we can monitor the temperature here, and once it hits 80 degrees Celsius, the alcohol vapors will travel up. They're going to travel across this tube, and there is water on the outside, so we're condensing the vapors back from the gas to the liquid phase. So we can collect our pure alcohol in a flask on the right, and the water would remain in the flask on the left. Chromatography is another technique we can separate solutions with. For example, if we had food coloring, which in these examples here are all mixtures of different pure substances. So we could start with maybe red food coloring, and when you use a solvent, you could use that to separate it into the different colors. So maybe this one came from pink and red, which were the pure substances used to make that food coloring. Solubility is the maximum amount of a solute that will dissolve in a solvent at a constant temperature. This solubility is unique to different substances. For example, the solubility of salt is 36.2 grams per 100 grams of water at 25 degrees Celsius, which is around room temperature. So imagine I have a glass of water and it contains 100 grams. And I'm adding salt to it. I can add 36.2 grams of salt to it. If I added more salt, I'd have a solution that looks like this. So this would be my salt sitting at the bottom. The liquid portion up here would be what I call a saturated solution. If I add more than 36.2 grams, it's going to separate from the bottom. That water cannot handle holding any more salt. An unsaturated solution is one where the solvent contains less solute than it can hold. So for example, let's say this glass on the left, I have 100 grams of water in here, and I add 25 grams of salt. I would classify that one as unsaturated, meaning I could add more salt, versus my saturated solution, the one on the right, is holding all of the solute it possibly could. Miscible is a term we use to describe when two liquids dissolve in each other in all proportions. For example, ethanol and water. That would be represented by my test tube in the center. If I have a solution that, let's say it's 80% ethanol and 20% water, they will dissolve in each other. If I have a solution that's 20% ethanol and 80% water, it's still going to dissolve. So it doesn't matter if I have more alcohol or more water, they're going to still dissolve in each other. So we classify that as being miscible. Immiscible is a term we use to describe when two liquids do not dissolve in each other. For example, on this test tube on the right here, we have two layers, so we'd call that immiscible. The one on the far left would be miscible because the two liquids that are in that test tube are completely dissolved in each other. Let's look at the effect of temperature on the solubility for when we have a solid or a liquid dissolved in a liquid. It says the solubility is going to increase with increasing temperature. This graph below is illustrating the solubility of glycine, which is an amino acid, and this has our temperature on the x-axis getting higher, and then we have the solubility on the y-axis going higher upward. And this is for grams of glycine and 100 grams of water. So what the graph is showing us that at about 30 degrees Celsius, the amount of glycine we can dissolve is around 33.2 grams. And that's the amount in 100 grams of water. If we increase the temperature up to 80 degrees Celsius, we can dissolve about 52.8 grams of glycine in 100 milliliters, or we can say that's 100 grams. 100 grams is equal to 100 milliliters of water. And the way you can also remember this is maybe in your everyday life, you've put sugar into tea. So you can dissolve more sugar in hot tea versus iced tea. This graph is showing the effect of temperature on solids in water for their solubility. So again, as we increase the temperature, we can see that the solubility's trend is going upward. It is increasing as well. So remember the effect of temperature. Increasing temperature increases solubility for a solid or a liquid in a liquid. This chart is also showing us for different compounds that they do have different solubilities. So for example, sodium chloride has a different solubility than potassium nitrate. Let's look at the effect of temperature on solubility for a gas in a liquid. So the solubility of a gas in a liquid decreases with increasing temperature. So this is the opposite effect of our solid and liquids in a liquid with temperature for gases. So this graph below is showing us the solubility of oxygen, which is a gas, in water, our liquid, at various temperatures. And we see the opposite effect on our graph. So as we increase the temperature, the solubility of our oxygen is decreasing in water. One example in our everyday life is thermal pollution. This is where the water is going to be unnaturally heated, and it causes the decrease in the solubility of oxygen. So for example, where nuclear power plants are, they're usually by a body of water, and the heat that's coming from that power plant might be unnaturally heating that water source. And what happens is there's oxygen in the water, and the fish need oxygen to survive. So if the water is unnaturally heated, the oxygen solubility is going to decrease, and so there won't be enough oxygen for the fish to survive. Let's look at the effect of pressure on solubility. For solid and liquids, in a liquid, pressure has little effect, so we don't need to worry about that. However, for gases, the solubility in a liquid increases with increasing pressure. As an example, we have a can of soda here. Soda is bottled under pressure because that increases the solubility of the gas, which is carbon dioxide. So we can dissolve more carbon dioxide because of the higher pressure in our solution of soda. When we open the top of it, we release the pressure, so we're coming to atmospheric pressure. So it's a lower pressure. So the solubility is going to decrease when we decrease the pressure. And you can see there's less molecules in the can on the right, and we've lost those molecules to the atmosphere, which is also why we hear that whoosh sound when you open the top of your soda. This graph shows the solubility of carbon dioxide, which is a gas, in water based on pressure. So as our pressure increases on the x-axis, our solubility increases as well, which is represented on the y-axis. This is for carbon dioxide gas, which might be an example of CO2 in bubbly water. That again, we increase the pressure, we can dissolve more gas in that water. Another example in our everyday life that shows how increasing pressure increases the solubility of a gas is in scuba diving. So this graph is showing us here that I have grams of nitrogen, and I'm going to look at the solubility. As I increase the pressure of the gas, the solubility is increasing upward. And in air is comprised of mostly nitrogen, and we need oxygen. So scuba divers wear this tank on their back of supplied air, which has nitrogen in it. So it's just showing you that the solubility will increase when you increase the pressure. So the gas solubility is increasing in a liquid. So what happens when you're scuba diving? The pressure on your body is going to increase from the water around it as you descend. So my scuba diver here is at sea level, so the atmospheric pressure is 1. As we go underwater, we're descending down to 10 meters. The atmospheric pressure increased to 2 atms. So we've increased the pressure of our gas. So we've increased the amount of nitrogen and oxygen that can be dissolved in our blood supply. So we've increased the solubility of the supplied air gases in our bloodstream. So that means we're breathing in more air when we're underwater. When the diver ascends or comes back up to the surface, the pressure on the body decreases and the solubility of our gases in our bloodstream is also going to decrease, which can cause gas bubbles to form from that excess air that we have in our bloodstream when we're down below. If we go to the surface very slowly, we're going to exhale the bubbles, the excess air, and we diffuse those excess bubbles through our skin. If we come up too fast to the surface, then the bubbles will stay in the bloodstream, preventing blood circulation. And this results in a condition that's called the bends. And people could actually die from that if you stop your blood circulation. The bends can be treated by putting the person in a decompression chamber to bring them back to a pressure at a more slow pace.